Hello, welcome back. I'm so glad that you're all here. So today we're going to talk about 7.1, which is exploring quadratic relations, which is really going to be the intro to this whole topic. There are kind of a few definitions that we need to get through first, just to make sure that we understand the terminology and all the things and such. But after that, we're going to jump right into some math. So it's going to be dope. So, for starters, a quadratic polynomial. Remember polynomial? Poly means many, and then nomial talks about all the terms that are involved. So it's just something with many terms. But a quadratic polynomial is a polynomial, believe it or not, of the form y is equal to ax squared plus bx plus c, which looks really familiar to all of the factoring things we looked at the other day. So that's dope. A couple of things is that a, b, and c are just real numbers. Right, so they could be decimals, they could be fractions, they could be positive, they could be negative. The only thing, or the only kind of major restriction, is that a cannot equal to 0. Because if a is equal to 0, then we have 0 times x squared, which is just 0. So we only have bx plus c, which looks more like a line than anything. So a can't equal to 0. This is our nice fancy function form of the same thing. And life is good. Couple of little tidbits about quadratic polynomials. Tidbit number 1 is that quadratic polynomials have a degree of 2. Right, so if we're looking at all of our variables, the highest power on that variable will be 2, and that makes it quadratic. Another little tidbit is that the graph of a quadratic is called a parabola. It is a curve that kind of looks like this, or like that. We're going to be talking more about parabolas and their kind of special features down the road, but it is a curve. It is not a line like you would have seen in a linear relation, but that shape is a unique shape, and it's called a parabola. So you could look at it and kind of look at its little cute little smiley face, or a frowny face. Sadness. Anywho, last thing about our little quadratics here is that parabolas, well, they can open upwards into our little smiley face, or downwards into our kind of sad face there. They can vary in width and steepness. But they will always maintain that curved shape. Alrighty, so the have a degree of 2, the graph is a curve, and that curve is called a parabola, and that parabola will open either upwards or downwards. They will vary in width, so you could have a parabola that's crazy wide or super narrow. If you have something more narrow, that means it's going to be a little bit more steep, right? If you have something more wide, it's going to be a little bit less steep, right? They can vary, but they always maintain that curved shape. All right. Something just to keep in mind here is that degree of a polynomial. We already said that a quadratic polynomial has a degree of 2, but let's just kind of think back here. What does a degree of a polynomial really mean? Well, it's the largest sum of the exponents on the variables in a single term. Of that polynomial. So, for example, if we look at the 3 equations or the 3 polynomials below, we are going to look at all of the variables. We're going to look at the y's, we're going to look at the x's, and we're going to look at each term. Reminder that terms are split up by our plus or minus signs, or even the equal signs there. So this is a term, this is a term, this is a term. There are 3 terms here in this first equation. For my first guy here, y has the exponent of 1. My second term, x, has the exponent of 1. My third term, there's no variable, so my highest sum of the exponents on a single term would be 1 here. In my quadratic, my y has an exponent of 1, my x has got a 2, my x has a 1, and my c's got nothing. So my degree of a quadratic is 2. And for my cubic equation, my y has an exponent of 1, my x here has an exponent of 3, my x there has an exponent of 2, my x here has an exponent of 1, and there's no exponent on a variable existing in the last term. So my highest exponent is 3. So a cubic will have a degree of 3. Okay, so again, we're looking for the exponents on our variables, and whatever the largest sum is going to be our degree on that polynomial. Quadratics will always have a degree of 2. Alrighty. We're also going to be talking about domain, and we're going to be talking about range, and hopefully those are things you're feeling pretty decent about as well. As this unit goes on, we're going to be using domain and range a good chunk, and we're going to be using it quite a bit next year as well, so that's something to have a good grasp on. Once we get to that point in the unit where we're using it a little bit more than just kind of your basic domain and range, we'll go over all of the fanciness of set notation, all the fanciness of interval notation. But for now, we're just going to define it so we have the definition to refer to. The domain refers to the complete set of possible values of the independent variable. So that's the variable that's usually graphed on our x-axis. A lot of the time we refer to it as x, but sometimes we use other letters. And it's always recorded from lowest value to highest value. Particularly when we're talking about interval notation. The range is quite similar, except this time the range is actually going to be the complete set of possible values of the dependent variable which again is usually our y, but if not y, will be found on our y-axis. And it is always recorded from lowest value to highest value as well. particularly in interval notation. Okay. So when we talk about domain and range, we can either write them in interval notation or set notation, like I said. Whenever we do examples together throughout the unit, I will be showing you both. But either will work, so if you have a preference, you are more than welcome to stick with it. I will not ask you specifically for interval notation. I will not ask you specifically for set notation. I will just say, tell me the range, tell me the domain, do y'all thing. Okay? Alrighty. So what we're going to do is we are going to look at some graphs of quadratics. The simplest graph of a quadratic, we could actually call this guy the parent graph, is when we have y is equal to x squared. Right? So our a value is 1, our b value is 0, and our c value is 0. Okay? So what we're going to do is we are going to make a table of values to figure out some points that we're going to plot. We're going to graph it below. We're going to figure out the domain, the range, y-intercepts, x-intercepts, the whole 9 yards. It's going to be dope. So, our x values, I've already picked some out for us. We're going to talk about the x values from -3 to +3. But we need to figure out the y values. Since our y is equal to x squared, we can go ahead and figure out, well, our x here is -3. -3 squared is +9. -2 squared is +4. And so on and so forth. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 2. And 3 squared. Oh, 2 squared is not 2. Silly me. 2 squared is 4. Dodoy. And 3 squared is 9. Okay. Notice that when I started plugging these guys in, I always put my value inside brackets. I do that as a habit, especially when I have negative numbers, just to make sure that that negative is also being squared. It's that whole value -3 that's being squared. Sometimes if we forget the brackets, we get into the silly mistake of saying, well, -3 squared is just negative times 3 squared, which is negative times 9, which is -9. And that would just be a little bit silly. So what we're going to do is make sure that when we're plugging in values for x or y or whatever down the road, we're going to make sure that we're always plugging that in brackets to make sure that we avoid those silly mistakes. We're going to go ahead and graph this now. We're going to graph this down at the bottom of the page. Notice that our x-axis is labeled, our y-axis is labeled, we've got a scale going on. Life is good. And when we do this, we are going to go ahead and start graphing and plotting our points. So our first one that we had was the point -3, 9. So we plot -3, 9 to be up here. Then we have -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. Now, we are going to connect these dots, but we're going to do so in a curve, because if you remember, the graph of a quadratic is a curve called a parabola, which means we are not making straight lines between each of these because that would be incorrect. We are going to draw a smooth curve, and to the best of our ability. Okay, just pro tip here, use a pencil. Sometimes you make a curve and it's wonky as can be. I am not a stranger to that feeling. So please use a pencil. That way if it's wonky, that you could erase it and redo it. Because if it's too wonky, you could actually lose marks. And who wants to do that? So we're going to go ahead and draw in a beautiful curve. Oh yes, how lovely. And it'll extend past. Whew! Now try and mirror that on the other side. My left half is always the nicer half of my curve drawing. Although my right today is just maybe taking the lead. We draw arrows at the end of these graphs because if we were to continue on, say we had the point x is -4, well, -4 squared would give us +16. It would continue going in either direction. So that's something that we would see and we would keep on graphing. So we do that with an arrow to indicate that it would go on. I want to see if I could pull up the thing they call Desmos. Tra-la-la. Oh, why hello. See if I could just, I'll do a little bit of split screen on here. So, if we wanted to graph this on Desmos, just to make sure, like, keep us on track here. Are we doing the right thing? Notice that our graph looks just like their graph. Honestly, I'm a little biased here. I'm going to say ours looks better. But notice that they don't have arrows. Okay. Keep in mind here that they don't have arrows because their graph literally doesn't end. If you do all of the zooming you want, it'll just keep on going. So, yes, ours has arrows because we don't keep going. If we wanted to graph this forever, we would live our whole life graphing it, pass it on to our children, die, and still not be done. Anywho, yeah, we'd be graphing forever. What a legacy. So, we are going to take a look at the domain. We're going to take a look at the range, the y-intercepts, the x-intercepts, all that jazz. And now that we have the graph, we can actually visualize that. So, in our domain, because we have arrows on either side of the graph, it continues on either direction. Even though the arrow looks like it's going straight up, it's going straight up and to the left. And here it's going straight up and to the right. So if I'm trying to look for the furthest left point, well, it would continue all the way down to -infinity. And if I'm looking for the furthest right point, or the largest value, that would continue all the way to +infinity. Okay? So our domain is literally any possible value of x, so from -infinity to +infinity. We use soft brackets with infinity because infinity can never be included. Just when you think you got it, soik, you can't grab it. So soft brackets are always used for infinity. If we wanted to do this in terms of set notation, we would use our set brackets. So the set of, we're talking about the variable x, such that, is that vertical line there, and x can literally be any number as long as it's a real number. So we say x is an element of the real. Our range is a little bit of a different story. Our range talks about our y value. We always go from lowest to highest, so bottoms up. Our lowest value here, if we take a look at our graph, is actually that the y value of 0. Okay, and there's a point that actually occurs on the y value of 0. So 0 is going to be included in our interval, which means it gets a nice square or hard bracket. And as we can see, our arrows indicate the largest value continues on forever. So it goes all the way to infinity, and we use a soft bracket with infinity. If we wanted to do that in set notation, we would start it off like we normally do. The set of, we're talking about the variable y, such that y has to be greater than or equal to 0. And y is, again, an element of the real. Next piece. How many y-intercepts actually exist here? Well, a y-intercept is when we have a point on the graph that either touches or crosses that y-axis. That happens once. And that happens at the point 0, 0. That happens when y is equal to 0, or we could say 0, 0. We could express them in either way. And here we only have one x-intercept as well. Remember, an x-intercept is where the graph touches the x-axis. It doesn't actually have to cross the x-axis. So that happens, again, at x is equal to 0, or the point 0, 0. Noise. We can do the same thing with this next graph here. Here we have y is equal to negative x squared. So the negative is not included in the squaring portion because there's no bracket involving it there. So here we can do the same thing as what we did at the beginning. We can plug in all of these predetermined values of x, determine what our y value would be. So we have negative 3 squared, which would give us negative 9. Negative 2 squared gives us negative 4. Negative 1 squared gives us negative 1. Negative 0 squared is 0. Negative 1 squared, which is negative 1. Negative 2 squared, which is negative 4. And negative, ugly 3 squared, which is negative 9. So essentially the same numbers, except all negative, which can be anticipated because that's the only difference in the equation. It's the exact same equation with a negative slapped on in front. So we're going to go ahead and do the same thing. We are going to graph all damn points, dough. So here we have negative 3, negative 9. We have negative 2, negative 4. Negative 1, negative 1. 0, 0. 1, negative 1. 2, negative 4. And 3, negative 9. We are going to connect those dots by drawing in a nice parabolic curve. Right? Because we're not connecting them with lines. This isn't connect the dots like you would have played back in the day. This is beautiful math. So we gotta use extreme care and love. So we are going to connect the dots in a nice curvy way, and if we screw up, we're just going to backtrack and try it again. Yeah, that's not nice. I'm going to maybe zoom in to see if I could do a better job. Yeah, not bad, not bad. Try the other side. My weakness. Oh, see? All right. I've seen better. I've seen worse. Similarly, while you're just finishing graphing that here, I'm going to hit up the Desmos, I think. If I can whip this up here. And I'm going to graph the same thing so we can make sure ours looks similar. I noticed that mine looks a tad lumpy, but it's not ridiculously lumpy. Things that your graph shouldn't look like obviously lumps and bumps here, that would not be ideal. You want to make it as perfect as possible without obviously spending hours and hours trying to figure out the most ideal drawing of it. But it should represent what the graph should look like. Okay? You're welcome to use Desmos to make sure that your graph looks the same. In fact, that will be a tool that we will be using throughout this course. So it is not cheating. It is just a tool, like using a calculator. All right. We have arrows at the end of our graph, just like we did in the first drawing, because just like if we look at Desmos, this does continue on. That's why they don't have arrows on theirs. We could scroll on forever and still see that graph. But we're not going to do that on ours because we're just going to draw arrows and say, yeah, keep going. Okay. We are now going to be talking about the domain, the range, the y-intercepts, the x-intercepts, all of those things. So, our domain, because we have the arrows on either side, continues all the way from negative infinity to positive infinity. And just like we did before, in set notation, that would be the set of all x such that x is an element of the reals. Our range in this case, remember we go bottoms up from the smallest or lowest value of our y to the highest. We go all the way down from negative infinity and we peak at 0. So our range will be negative infinity all the way to 0. 0 is a point on our graph. It is included. So we include it using a hard or square bracket. And when we're doing our range here, we have the set of all y such that y in this case is less than or equal to 0. And y still has to be an element of the reals. Here we have one y-intercept. And that is the same y-intercept as we had before, where y is equal to 0. Or we could identify it as the point 0, 0. We have the same number of x-intercepts in this case, which is 1. And it's the same x-intercept as before. It's our origin, 0, 0. Did you feel? Aye. Woo! Graphing! We have 2 examples left. Same ideas that we're going to make a table of values. We are going to graph them. We're going to check on Desmos. We're going to pat ourselves on the back for doing a good job. And then we're going to call it a day. Okay. What we're going to do is we're going to actually do all this math to figure out all of these different points. I've pre-selected some points for us so that we could take a look at what they look like. I don't know. And then, yeah, we're going to graph them. So let's go ahead and do that. Here we have the equation y is equal to 2x squared minus 5x minus 6. So a little bit more involved than just y is equal to x squared. We've got some a, b, c values that aren't 0 or 1. But we plug it in just the same. If we wanted to find the y value when x is negative 3, we plug in a negative 3 every time we see an x. Oops. And we solve. So we have 2 times negative 3 squared. Negative 3 squared is 9, times 2 is 18. Negative 5 times negative 3 is going to give me a positive 15, and then negative 6. Then 18 plus 15 minus 6 will give me 27. What I want you to do, pause this video as soon as I finish telling you the instructions, is I would like you to go ahead and figure out your y values for every single x term remaining. Okay? Once you figured those out, double check that they're all the same as mine, and then go ahead and we'll plot them together on the graph. Okay? So pause now. Did you do it? Oh, phew. Good. Welcome back. Oh my gosh, I've missed you so much. So we're going to do the same thing. We're going to maybe show the work for the next couple. So 2, plug in negative 2 squared minus 5 times negative 2 minus 6. That gives me 8 plus 10 minus 6, which gives me 12. I don't know. Maybe I'll do the next 2 just for the sake of you seeing what it looks like plugged in, to confirm that yours looks the same. And one more just for funsies here. Oh, so fun. I know. Alright, so hopefully that's what it continues to look like on your sheet. The last 3 I'm just going to plug in or give us the final answers here. If you are curious to see that work, how it looks plugged in, I did post the notes key online, so you could take a look at there. I have all the work shown, but these are the values that you should get. Okay. What we're going to do is we are going to plot all of those values that will fit on our graph onto our graph. So we have our x and our y axes labeled. We have our scale indicated for us. Right now, we're going to start plotting. Our first point is negative 3, 27. And girl, I'm going to tell you, we don't have room for that. So, nice try. We're not graphing it. The next one, negative 2, 12, technically not on our graph, but just for the sake of kind of having an idea, why don't we just draw a dot where we think that should be. Next, we have the point -1, 1. I think I drew this a little bit off to the side here. My apologies. Oh, so nice. Okay, -1, 1. So we're going to get a point-ish around there. Not ish, exactly. Then we're going to get the point 0, 6. So here we go. 1, -9. 2, -8. And 3, -3. Now, you might be thinking to yourself, how the heck do I draw this parabola? Right? The other ones that we drew were fairly symmetric looking. And in fact, all parabolas are symmetric. So if our points aren't, that doesn't mean that we did something wrong. Oops. How do I move this? What if? Oh, blah-blah. Okay. That just means that maybe it's not symmetric on a beautiful, nice point. So here, I'm going to plug in our equation here. And this is what I get. See how it looks nice and beautiful? Well, our vertex here doesn't happen on one of those nice, beautiful points. Our vertex are... Oh, I don't like this. Hold on. Okay, Desmos, I've had enough of you. Just kidding, come back. Alright. So, our vertex is at that 1.25 as an x value. So our vertex is happening somewhere around there. So when we draw this, we're still drawing this nice curvy shape, but it's not maxing out at one of those places there. So let's go ahead and do our very best to draw in this nice curve. Oh, I'm already failing here. That's okay. No harm in restarting. And it continues on. I'm going to draw arrows at the end. And I'm going to do the same thing on the other side. And that turned out much better than I anticipated. But yeah, so now we have our parabola. It looks like what Desmos is showing us here. Life is still good. And again, like I said, we could use Desmos as a tool to make sure we're on the right track. Last example! Whoop whoop! Alright, for this last example, same sort of idea. We've got some x values predetermined for us. We are going to plug them in. We are going to solve for our y values that match or correspond with those x values. We're going to graph it, and it's going to be beautiful. So, I'll plug, 1 in for you. So we have -3x squared, which is -3 squared in this case, plus 6x, which is 6 times -3, minus 4. -3 squared is positive 9. 9 times -3 is going to be -27. 6 times -3 is -18. And minus 4, that should give us -49. I want you to continue on, get all of those values for our y coordinates below. And pause. Unpause. Welcome back. So, as you went ahead and plugged those in, so did I. And I ended up getting -28, -13, -4, -1, -4, and -13. Whoa, twinsies, you got the same? Dope. Alright, we're going to plot all those points that fit on our graph here. Notice our graph has our x-axis labeled, our y-axis labeled. We've got this beautiful scale going on. Ooh, baby. So, we are going to take a peek. We're going to start and plot our point, -3, -49. Yeah, best of luck. We're not plotting that. What about -2, -28? Oh, no, not really a chance there. But what about -1, -13? Again, doesn't really fit on the graph, but just to kind of have an idea of where it would be, let's do it. And it would be ish there. Okay. 0, -4. Oh, we could plot that like nobody's business. 1, -1. 2, -4. Oops, ugly kind of dot there. And 3, -13. Okay. And again, if we want to take a peek at Desmos to confirm that we're doing a good job, which, trust me, we are, we can go ahead and plug that in. Y equals 3x squared. Oh, sorry, minus 3x squared. Minus 3x squared. Plus 6x minus 4. And we can see that the vertex occurs at 1, -1. And so we can go ahead and draw in our parabola on either side. Beautiful. The one thing I want you to be careful of, even when we get here, you don't want to draw like a peak or a point or a corner. You want to still try and make it smooth looking, even though it might be a little bit of a tight turnaround, especially for your vertex, because this is a curve. It's not a collection of lines that come together. So you want to try and make it smooth at the top, no matter how difficult that might be. All right, for 7.1 homework, you've only got 2 questions there, and honestly, you're pros now, so shouldn't take you very long. I believe in you, and that's all. Peace out, homies!